Well, hello again everybody. Now I'm sure you'll remember at the end of last year I said that I'd like to do some more construction projects and also look at a little bit more test equipment this year. So we're going to start off our new year by doing that. So we're going to be looking at some test gear and we're going to be doing a simple construction project. Well, it's actually quite a few years ago now, but I went ahead and I built this Velleman audio signal tracer kit, and it's actually been fairly useful and I've used it quite a bit for debugging amplifiers and radios, but it does have some limitations. So what we're going to be building today is we're going to be building something called an active demodulation probe, and I'm going to talk about that and what it does a little bit later. But before that, I'm actually going to step back to another video that we made where we talked about input impedance of pieces of test equipment and the effect that that can have on your circuit under test. So let's dive into that to start with. Now previously, I'm sure you'll remember that we did a bit of a restoration on this vacuum tube voltmeter, and in that video we actually discussed that different types of meters, they have what they call different input impedance. Now what that actually means is that when you're actually trying to measure a voltage on a circuit like this one, for example, depending on what type of voltmeter you use, they will actually impose a load on the circuit. And the problem is if you start putting a load onto the circuit, the voltage can fall. So depending on what type of meter you use, you can actually get different voltage readings. But I actually wanted to go ahead and show you that because we kind of run out of time in one of the previous videos. So you can see I've got a piece of circuit board here, and I've gone ahead and I've actually just soldered some resistors onto it, and I've put some terminals on each side of our resistors here just so we can put our test probes on them easily. And these resistors, you can see I've arranged them in decade values. So the first resistor I've got here, we've got a 1 ohm resistor, 10 ohms, 100 ohms, 1 kilo ohm, then 10 kilo ohms, 100 kilo ohms, 1 meg ohm, 10 meg ohms, and then I'm afraid it does jump to 20 meg ohms because unfortunately I didn't have any 100 meg ohm resistors. So yeah, we go to 20 meg ohms. Now the top of the resistors here, you see all these terminals, all these terminals here, I'll just turn the board over, all these tops of these resistors here, they're all joined together, and they're joined together and they're actually connected to this red crocodile clip here, and this crocodile clip here goes to my bench power supply, and as accurately as I can I've gone ahead and I've dialed in that power supply to give a 10 volt output. So let's just have a look at that 10 volt output. So let me just confirm that I've got that voltage accurately set by just measuring the power supply voltage. So yeah, okay, you can see we've got 10 volts, and then on the tops of each of these resistors we should also have 10 volts. So there you go, 10 volts on that one. Okay, 10 volts on all of them. So yeah, that's not very exciting. So let's go back to our 1 ohm resistor and let's just measure the voltage on either side of the resistor. So of course we've got 10 volts on one side and we've got 10 volts on the other. That's no surprise, is it? Let's just have a look at the 10 ohm resistor. So again, 10 volts on one side, 10 volts on the other. Let's look at the 100. 10 volts on one side, 10 volts on the other. And let me just keep going. 1K, 10 volts, 10 volts, 10K, 10 volts. Okay, we no longer have 10 volts. Let's just double check, make sure there's nothing wrong with the power supply. Yep, got 10 volts there, but we don't appear to have 10 volts on the opposite side of the resistor. Let's go to the 100K. Okay, there's 10 volts on one side of our resistor. Oh, we've now only got 9.9 volts. So we've got some voltage gone missing somewhere, haven't we? That doesn't make any sense. Okay, let's go to the 1 meg ohm resistor. There's our 10 volts. Oh, now we're down to 9 volts. So you can see if we actually try to measure the voltage across this 1 meg resistor, we're actually losing a volt somewhere. Let's go to 10 meg ohm. There's our 10 volts. Oh, 5.2. So we've actually lost about, well, nearly 5 volts now. And finally, let's go to the 20 meg resistor. There's our 10 volts. And now we're down to 3 volts. Well, that was no good, was it? Maybe a bright yellow meter will work better, so let's try that. And 10k. Wow, our voltage has started to drop again. 100k. 1 meg. We've actually dropped a whole volt. Go to 10 meg. We're back to 5 volts, and at 20 meg we're at only 3 volts. So this meter doesn't work either. The problem is you can't trust this modern digital malarkey. I think we need to go old school. Okay, so we've got our 10 volts, that's what we'd expect on the input. So let's go on the 1 ohm. There's 1 ohm, yep, 10 volts, that's lovely. 10 ohms, still got 10 volts. 100 ohms, still got 10 volts. 1k, still got 10 volts. So this is working great, isn't it? Let's go to 10k. Oh, something's gone wrong there. This one's only measuring 9.5 volts now. Let's go to 100k. Now it's measuring less than 7. Let's try the 1 meg. Gone at 1 meg, it's only measuring 2 volts. This thing's worse than our modern digital meters. What on earth is going on? So let's see what happens if we try and measure the voltage across our 10 meg resistor. Wow, the needle barely even moves. So even our old school meter doesn't work. This is actually much worse than the modern digital ones. What's going on? Well, I've already gone ahead and tried pretty much every other voltmeter that I own, so we may as well go ahead and just try this vacuum tube voltmeter. So let's just check it reads 10 volts. And of course it reads perfectly. Let's shoot for our resistors. There's 1 ohm, 10 ohms, 100 ohms, 1k, 100k. So at 100k we're still reading spot on. Let's try 1 meg because we're about a volt under using the digital meters and we're considerably worse using the AVO meter. Well, it looks as though this meter is a lot better. It's maybe just a nudge under 10 volts there, so it has dropped a little bit but much less than the other meters. Let's try the 10 meg. 10 meg we're dropping just under a volt. At 20 meg it looks like we're dropping just under a volt and a half. So for whatever reason it does appear that even when we measure across a 20 megohm resistor using our vacuum tube voltmeter, the reading is actually an awful lot more accurate than it was using the modern digital meters. So that's a bit unexpected, isn't it? Well, as you've just seen, we did our testing there using 3 different types of voltmeters. We had the trusty old AVO 8, we had the Fluke digital voltmeter, and we had the Marconi vacuum tube voltmeter. And as you can see, for our 8 different decade resistance values, I've gone ahead and I've plotted the measured voltage from each of our meters. Well, looking at the table, you can see that all 3 of our meters actually compared very well with each other and measured correctly up to a source impedance of 1 kilo ohm. But as the source impedance increased beyond 1 kilo ohm, you can certainly see for the AVO 8 and the DVM, the actual meter reading seemed to divert away from the true measurement, which should have been 10 volts. So looking at the AVO first, you can see that at 10 kilo ohm source resistance, the voltage had actually fallen by half a volt. And the next measurement of 100k was almost half what it should have been at just over 6.8 volts. And things just kept getting considerably worse. So by the time we got to the 10 megohm, we were only actually measuring 0.2 of a volt, which is very wrong. Now you can also see that the Fluke DVM did actually quite a lot better. At 10k it was dropping just 0.01 of a volt. At 100k it was dropping 0.1 of a volt. At 1 meg it was dropping a volt. And at 10 meg again the reading's fallen by about half of what it should have been. So the meter that appears to be the most accurate was actually the vacuum tube voltmeter. Now you could see that the reading did actually change all the way up to 100k. So it was actually 2 orders of magnitude better than the AVO and the DVM meter. But at 1 meg it had dropped by 0.2 of a volt, and at 10 meg it still dropped by almost 1 volt. So finally, if we take a look at the source impedance vs the measurement error, and we'll just look at, for example, the 10 megohm resistor, we can actually see that the AVO meter, when we tried to measure a source impedance of 10 megohms, the error was 98%. You know, not far off 100% error. It couldn't really have been any worse. The actual Fluke DVM had an error of 50%, And it's interesting to see that the oldest voltmeter, which is a vacuum tube voltmeter, actually had the most accurate reading at only 9% error when we were measuring the 10 meg resistance. Let's go back to our A voltmeter and we can see that if we just check our supply here, we've got 10 volts, but if we go to the opposite side here of this 10 meg resistor, we've only got 0.2 of a volt because the meter, hopefully you can see that, the needle is barely moving. So we really are getting some serious shenanigans going on, but why? Now the idea of an analog voltmeter is somewhat of a misnomer because an analog meter movement like this, it doesn't actually measure voltage. What it actually does is it measures current flowing in the circuit. So what we have here, we've got a needle pointer, and that needle pointer is connected to a coil of wire, and that coil of wire is free to move within a magnetic field. So when we connect our A voltmeter into circuit, what's actually happening is we're taking some current from that circuit under test, and that's being used to magnetize the coil of wire within the meter movement, and that magnetic field repels the needle and makes it move. But the important thing to know is that the meter movements itself, the actual power needed to make the meter move, that comes from your circuit under test. But unfortunately, when you connect the A voltmeter to a circuit that's got a very high impedance like this one, 10 megohm, we can't actually draw enough current through that 10 megohm resistor to make the meter movement operate. Now of course it's bad that we're not able to get an accurate voltage reading from our 10 megohm resistor here, but it's actually far worse for the circuit under test. Because we are drawing current through this resistor, of course we're getting a very high volt drop. So of course if your circuit needed to operate at 10 volts, as soon as you connect the A voltmeter to it, it's dropped to about 0.2 of a volt, so it's quite likely that your circuit here would now no longer operate. Now to help illustrate what's going on, I've gone ahead and I've set up a simple circuit simulation. So you can see on the left here we've got what I've called a perfect voltmeter. Now the perfect voltmeter is actually connected to plus 10 volts through a 10 megohm resistor, and you can see that our perfect voltmeter is actually indicating 10 volts, and you can also see in circuit we've got a micro ammeter current meter. Now because our perfect voltmeter is in fact magic, it doesn't actually draw any current, and that's indicated by the fact that our microammeter indicates 000, and because we have no current flowing through our 10 meg resistor, well, according to Ohm's law we're not going to get a voltage drop across that resistor, so we can see that we have 10 volts appearing on the terminals of our voltmeter. But unfortunately in the real world things don't quite work out so well. So this time I've gone ahead and I've actually modelled our analog A voltmeter, and as we did for the perfect voltmeter, we've connected the A voltmeter to a 10 volt supply via a 10 megohm resistor. But now you can see the indicated voltage is only 0.2 of a volt this time rather than the 10 volts for our perfect voltmeter. And you can also see that our current meter is indicating 0.98 microamps of current. So that 9.8 microamps of current is flowing through our 10 meg resistor, and it's actually flowing into our meter to actually provide power to move the meter movement. Because we now have current flowing through that 10 megohm resistor, according to Ohm's law we're going to get a volt drop, aren't we? So using Ohm's law, if we take our 0.98 microamps and we multiply that by 10 megohms, that actually gives us a voltage reading of 9.8. So that's 9.8 volt that's being dropped across a 10 megohm resistor. So that actually means there's actually only 0.2 of a volt left for our voltmeter to indicate, because the voltage has been pulled down from 10 to just 0.2 of a volt. In the case of an A voltmeter, the actual movement draws very little current, and so it's actually necessary to install a resistor in series with the meter movement just to protect it so we can't get too much current flowing in it. For an A voltmeter, the approximate resistance used in series with the meter movement on the 10 volt range, it's actually around 200 kilo. Now that value of 200 kilo, it's actually derived from the AVO's meter sensitivity, which is listed as being 20,000 ohms per volt. So the way that you work out the resistance across the AVO's terminals you need to know the voltage range that you're on. In this case it's 10 volts. You multiply the 10 volts by the meter's sensitivity, which is 20,000 ohms per volt, and what that will give you is that will give you the approximate resistance across the meter movement. Now in this case it's 200k. So another way you can think about this problem is we've now got a 10 megohm resistor which is in series with a 200k resistor, and of course we call that a voltage divider. So the voltage is actually going to get divided down by the ratio of R2 and R3, which in this case is a divider ratio of about 50 to 1. Now in the case of our final two meters, which are the digital voltmeter and the VTVM vacuum tube voltmeter, the indicated meter readings were quite a lot higher. In the case of a DVM it was 5 volts, and for the VTVM it was 9.09 volts. Now the way in which the DVM meter and the VTVM operate are actually quite different than the way that the AVO meter operates with its analog meter movement. In the case of the digital voltmeter, the input is usually connected via a field effect transistor, a FET. Now in the case of our vacuum tube voltmeter, the input is actually connected to an analog meter movement, but it's connected via the grid of a valve. And in both of these cases, whether it be the field effect transistor or the grid input of the valve, both these devices are actually voltage operated devices, unlike our analog meter movement, which is a current operated device. Now in theory, because these devices are voltage and not current operated devices, they shouldn't actually draw any current from the circuit under test. But you can see by looking at the voltage reading and actually the current flow in both of the circuits that some current is being consumed from the circuit under test. So both of these meters do obviously have some input resistance. Now in the case of a digital voltmeter, typically that input resistance will be about 10 megohms. Now I did actually do a little bit of digging online to try and find out why the input resistance of a digital voltmeter is 10 megohms, and to be quite honest I wasn't really able to find a good answer. Now for a field effect transistor, the actual input resistance of the device itself can really be very high, certainly in the hundreds of megohms and probably in the gigohms value. But for some reason 10 megohms was actually chosen, and what you'll actually find is that there is actually a 10 megohm resistor effectively wired across the terminals of a digital meter. Now it isn't really clear why they used 10 megohms. I suspect it's because it was chosen for practicality. If the input resistance of the meter was very high, probably the digital reading would float around, and that could be misleading. Whereas if they'd used a very low measurement resistance similar to the AVO, they would have had the problem that it would load the circuit under test. So I'm guessing that the value of 10 megohms was kind of just decided rather arbitrarily, and after the decision to make one meter 10 megohms, I'm sure that a lot of manufacturers just followed suit. So you can see that our 10 megohm resistance for the digital voltmeter, it's actually the same value as the source impedance R4, so we're going to get an equal voltage divider. So for that reason our 10 volts is being divided in half to just 5 volts, and that's pretty much what we saw when we took the real measurements. Now in the case of the VTVM, the grid resistance of the valve again can be in the hundreds of megohms or in fact in the gigohms, but for this particular meter the input impedance was chosen at around 100 megohms. I think it's actually 104 megohms, and because the input impedance is so high to 100 megohms, the actual current flowing in our circuit is very low, and so very little voltage is dropped across the 10 meg resistor. In fact in this case we drop just 1 volt. So in some ways it doesn't really matter whether you spend a few pounds on an analog meter or a few £1,000 on a very advanced digital voltmeter. If the source impedance of your circuit under test is very high and the resistance of your meter is relatively low to that source impedance, you're going to get inaccurate measurements. Now I'm sure in the past that some of you have looked at the service instructions for equipment like valve radios, and it's quite typical to find within the service instructions a description of the type of voltmeter that was used to take any kind of measurements. And so of course it's quite important to try to use the same type of meter as is indicated in the service sheet. or you'll find that your voltage measurements could be different to those indicated. Now I'm sure that there's some of you thinking that this problem with input resistance and impedance doesn't really affect me because, you know, I'm not using some crusty old Avo meter like this. I've got some flashy, all singing, all dancing oscilloscope on my bench. Well, I'm afraid if you did think that, you would actually be wrong, because as you actually increase the frequency of the signal, if you actually move away from DC and move into AC, and especially at RF signals, at the moment we're looking at a signal here on the oscilloscope at 20 megs, the problem becomes even worse with the oscilloscope loading our circuit. So what I've done is I've actually disconnected the DC power supply from our source resistance board here. I've disconnected that, and in place of the DC power supply I've actually connected my RF signal generator, and we've actually got it terminated here across a 50 ohm resistor so that the output just see a correct termination. And I went ahead and set the signal generator to about 20 megahertz, and at the moment I've got the scope probe connected to the output from our 1 ohm resistor, and just looking at the scope here, it's indicating about 190 millivolts. It's flicking around slightly. So let's go to the 10 ohm resistor, and you can see even with just the 10 ohm resistor in circuit, the voltage has actually dropped a little bit to 186 millivolts. Let's go to 100 ohms. Had quite a significant drop there, so we're now only at 132 millivolts. Let's go to 1K. And another big drop. In fact, we'll have to just adjust the sensitivity of the scope. So there's a massive drop. At 1 kilo ohm, we're only at 34 millivolts now. And at 10 kilo ohms, the signal has pretty much disappeared altogether, or certainly it's dropped back into the noise. Now, in a similar way to taking our DC measurements, what's actually going on is when we actually touch the scope probe, for example to this 1K resistor, again it's actually forming a potential divider between the 1K of source impedance and actually the resistance, or I'm going to call it the impedance of our scope probe here. Now for our DC measuring equipment, the resistance, if you like, was fairly constant, especially for the DVM meters. It was fairly constant at about 10 megohm. Now unfortunately the actual loading of a scope probe is considerably worse than that, or it can be worse than that, and the effect that we're actually seeing is, rather than the circuit being loaded down by the resistance of the scope probe, it's actually being loaded down by the capacitive reactance of it, because scope probes have some capacitance. Now I'm sure some of you will remember the formula 1 over 2 pi fc, which actually gives you the value of capacitive reactance, but for this particular scope here I've got it set to what they call the ×1 setting, which is as bad as it could be really. That's why I chose to use a ×1 probe. So we're actually introducing about, I think it's about 95 picofarads of capacitance. So what we have is we have a capacitor, a 95 picofarad capacitor now in series with our 1K resistor. Now of course at DC the capacitance isn't a problem, but when you've actually got a circuit with, as this one has, with a source frequency of about 20 megahertz, if you take 20 megahertz, plug it into the formula with a 95 picofarad capacitor, that's got an effective impedance of about 80 ohms. So actually what you've got is you've got a 1K resistor in series with an 80 ohm resistor, so of course it's going to load up the circuit very, very considerably. Now unfortunately, if we were to actually increase the frequency of the signal generator, we would actually find that the loading effect by the oscilloscope probe would actually get even worse, because the capacitive reactance, or the equivalent resistance of the probe here, it will fall as the frequency increases. Now for this video I'm not going to get into a long discussion about the impedance of scope probes, but basically all you need to know is if you have a scope probe with a ×1 setting here, you don't ever want to use that for measuring really AC waveforms at all. I mean, you can use ×1 maybe up to a few kilohertz, but you certainly don't want to use it beyond that. ×1 is really only to be used for things like DC measurements. So this oscilloscope probe also has a ×10 setting, which will actually reduce the effect of that capacitive reactance, and it will reduce the loading of your circuit. But even at ×10 probes, if you're actually probing again high impedance circuits or very high frequency circuits, you'll find that a scope will still put a considerable loading under your circuit on test. Well, I'm sure you'll agree I've probably spent quite enough time talking about circuit source impedances and how your piece of test equipment can actually load down the circuit and stop it from functioning as it should. You can get incorrect readings. Now, what that was all about, I've taken you on a rather torturous journey really to get to the main topic of today, which is this Velleman K7000 signal tracer. Now, I'm sure that most of you will actually be aware of signal tracers, but for those of you that don't, I suppose I'd better give you a bit of an explanation. So really, all a signal tracer is, it's quite a high gain amplifier, and you have a contact probe which connects the circuit that you want to look at. It connects it to the input of the amplifier, and then the signal tracer's also got a speaker inside. So basically what you can use this for, you can use this for tracing the audio through something like an amplifier or a radio. And what you would do is you would poke around various parts of the circuit and you would listen to the point at which the audio stops. Now, this is the K7000 from Velleman, and this is a kit, and I actually built this kit, it's actually a couple of years ago now. And I have to say that this Velleman kit is actually quite good, and I've actually used it quite a lot for testing radios. But what we've done is we've gone ahead and we've got our circuit board here with its various resistors, and at this time, rather than having it connected to an RF signal generator, we've actually got it set to an AF signal generator, and I've got the signal generator set up to give us an 800 Hz tone, so hopefully we can just hear that. So what I'm probing there is I'm actually probing the output from the signal generator. So we'll do what we did before, we'll go on to the 1 ohm output. Okay, that hasn't changed, same level. 10 ohms, just the same. Let's go to our 100 ohm resistor. Just the same. Let's go to a 1K resistor. Again, that sounds the same to me, but let's go to our 10K now. Now that's actually a little bit quieter. I'm hoping you can hear the difference. Let's go to 100K. And that's now a lot quieter. And now 1 meg. At 1 meg I can just about hear it. At 10 meg I can't hear anything. And at 20 meg I can't hear anything. So you can see again, I've not actually changed the amplitude of the source coming from our signal generator. It's exactly what it was set to before, which is about 20 millivolts. But we can't hear anything on this side of the 10 meg resistor. And again, it's because we're forming a potential divider between the signal tracer and our source impedance of 10 megohms. Now, if you're to look at the circuit diagram for this signal tracer, what you would actually find is the input is connected to the amplifier via a potentiometer, and that potentiometer, I think it's around 50 kiloohms. So the problem is we're actually forming a potential divider. So in the case of our 1 megohm resistor here, what we're actually doing is we're actually forming a potential divider between 1 megohm and our 47 kiloohm resistor in our signal tracer, and that's effectively dividing the signal level down by a factor of about 20 to 1. So although we might have 20 millivolts at our source here, unfortunately that 20 millivolts is actually being divided down. So actually the input to the amplifier of the signal tracer, it's only actually about 1 millivolt. So that explains why, the volume is just so much lower. Well, I'm sure you'll remember a few years ago we built one of these HX102 7 transistor kit radios, and these are actually very, very cheap little radios. I think I paid something like just £7 or £8 for this on eBay. And what I thought we could do is we could use our signal tracer probe, just have a poke round this simple transistor radio circuit and have a listen to see how well our signal tracer would work. But unfortunately, when I actually tried to tune in a signal on our little kit radio, it wouldn't work. The actual tuning control here, which I've taken off, it felt very stiff, and I thought, oh well, it's maybe just got a bit gummed up, maybe the label's dragging or something like that. But of course it was nothing that simple, so I've actually dismantled the thing and found out that this, I think they call this a polyvariacon cap, don't they? It's actually just completely puked its guts inside out. Well, I brought you on the camera to have a closer look. I'm hoping that the camera will focus, but can you see, if we look inside our polyvaricon, the actual plates, it looks as though there's some plastic material here, which, I don't know, that's maybe an insulator, it's a separator between the plates. Well, all that lot has just got all shredded and mangled up, and although I can just about turn it, it's actually just really stiff, and I think that all the plates are now shorting together. So yeah, I wasn't expecting to have to do a radio repair today. Now I'm going to admit right up front, I don't really do a lot of work with transistor radios, and that is where you tend to find these plastic polyvaricon capacitors, so I'm not exactly sure what the pinout is for these. I think that the central connection here, I think this is usually ground, and I think then you've got a capacitor section, a variable capacitor on each side, which is like a main tuning capacitor, and then you look at the back here and you've got a couple of smaller capacitors which are used for fine tuning. But yeah, I'm not exactly sure of the layout, and certainly there isn't a lot of information about this capacitor that comes with the radio. I think it actually says that it's something like 223 picofarads. I did try to measure that earlier, and I think because of its mangled state I wasn't able to do that. Oh, there we go, there's a reading, 73, does that change? That seems to go between 6 and 80 picofarads. Yeah, not sure what to make of that, but I'm sure it isn't working correctly anyway. So going through the junk box, I've actually just found another of these polyvaricons, and I am aware that these polyvaricon capacitors, they come in all sorts of different ranges of capacitance values. Unfortunately, I don't have the luxury of choosing the right one because this is the only one I happen to have. So it looks like one of our capacitor segments, it adjusts from, I think that's 15 picofarads all the way up to 160. Now I think if I just swap this to the other side, I think that's going to give us the other segment. So that goes from 7 picofarads but only goes up to 64. So I'm sure that these are actually designed to go in particular radio sets that need those particular values of capacitance, but yeah, it's all I've got. We're going to stick it in, see if it works. So I did actually have a quick look online for a replacement capacitor, and I pretty much found you can almost buy a kit radio for about the same price as getting a replacement capacitor. So I think what I might do, I might just buy another of these little kits. I think I did actually say at the time, I do recommend these little kit radios. I mean, as you can see, the quality isn't great, but they are really quite good fun to build, and certainly are educational. So yeah, I would actually recommend them. And it looks like we have got a wire here that's fallen off our ferrite rod, so we've got to put that on. Well, that sounds absolutely ghastly, so that's working normally. So I've gone ahead and I've tuned our radio into, I think it's something pointless like tennis. Let's have a listen. Hopefully you can hear that, and I'll just turn the volume down so we can just about hear it. I can hear something in the background, although it is a little bit scratchy. Now you can also see that I'm also using a different type of probe now. So this is what they call a demodulation probe. Now don't get very excited about the purpose of a demodulation probe. It really is quite simple. All we've actually got in here is a very sensitive diode, probably a germanium diode, and a capacitor. And the purpose of this demodulation probe, what this will actually do is, in the radio section part part of the circuit where we're actually looking at the incoming radio signal. That's, of course, it's an RF signal and it's modulated. So the purpose of the demodulation probe, well, modulation modulates the RF waveform, the demodulation probe demodulates it and recovers the audio frequency. So this will allow us to hear the audio content of an RF radio signal, but it will also work in the AF sections as well. So this radio has a push-pull output stage which is delivered by transistors V6 and V7. So we should hear an audio output from the signal tracer when we connect to the collector of V7. So let's try that first. Can you hear that? Okay, let's go to the collector of transistor V6 and we should get effectively exactly the same thing. Okay, so it looks like our output stage is working. So let's go to V5, which is a preamplifier which feeds the phase splitter transformer here. So again, let's go to the collector on that. And again, hopefully you can hear that. And I think that's just a little bit quieter than the actual output stage. Yeah, certainly I can hear the difference. So as you would expect, the signal at the preamplifier is a little bit lower, and of course we can tell that by listening to the signal tracer. So let's take a look at transistor V4 now. Now interestingly, transistor V4, it isn't being used as a transistor is normally used. They're actually only using the diodes in it, and what they're actually using the transistor as, they're actually using it as the detector stage. So it's not going to have any gain, it's just going to be used as a demodulator, much like the diodes inside our probe here. So let's see if we can just find the output from that.
For a third time, the dial leading 3-2 with the brake. Fifth and final set.
And that really is a lot quieter now. I can still hear it, but it is an awful lot quieter. So if I now find the base on this transistor, this should actually give us the intermediate frequency, so that will still be a modulated waveform, and our probe here is going to demodulate it for us. So let's see if I can get on the base.
Who's trying to win his second Grand Slam here in the early hours of Monday morning?
Okay, we can still hear that. So I'm now going to skip forward a couple of transistors because that's just the IF stage, and we're going to look at the RF input. Now the RF input again is quite interesting. It uses transistor V1, but transistor V1 actually fulfills a multiple of purposes. So it acts as an RF preamplifier, but it also acts as both the oscillator and the mixer stage. So it really is quite a neat little design. So let's go on to the base of this RF amplifier. And hopefully you can hear that when we actually make that connection to the base of the transistor, I'll just come off again. The radio does actually go silent, and the reason that the radio goes silent is because our actual signal tracer probe here, it's actually loading down the RF stage. It's probably loading it down, and probably the capacitance within the probe is also detuning it. So our radio doesn't actually work. So of course that really is quite a big problem. If when you're probing around in a radio circuit and your measuring equipment actually stops a piece of equipment from functioning properly, of course that's not good. You can't repair something if every time you touch your probe to it, it stops working. So the main point of this video is I wanted to talk about something called an active demodulation probe, which is something I've gone ahead and I've designed a little bit of a circuit for it, and really I think you will find it a very, very useful thing to work with this Velleman kit, because unfortunately the actual input impedance of this is actually so low, it's about 50 kilo ohms. It has an effect, it actually stops some radio circuits from operating. But if you're to build this active probe that I'm going to show you, not only will the active probe be an awful lot more sensitive, it also won't put as much load onto the circuit and detune it in the same way that a traditional demodulation probe will. So over the last couple of years, my K7000 signal tracer has actually had quite a lot of use. And I've used it for debugging audio frequency circuits and also for debugging RF circuits via a demodulation probe that I'd built. But I did find, particularly when trying to debug RF circuits, and especially those that had a relatively high source impedance, I found that the Velleman probe would actually load down the circuit and in some cases stop it working altogether. Now luckily I do have access to a Heathkit signal tracer, and that's got slightly more gain, and because it's based on valves rather than BJT transistor technology, the input impedance of that probe is actually considerably higher than the Velleman K7000 kit, and I have found that the Heathkit signal tracer does generally outperform the K7000. Now at the heart of my active signal tracer probe is transistor Q1, which in my case is a 2N5457. And for those playing along at home, that's a field effect transistor. The important thing to know about a field effect transistor, like a fermionic valve, is that it actually responds to voltage. It's a voltage operated device. Unlike, for example, a BJT or bipolar junction transistor, which is a current operated device. Now as the name suggests, if you use a BJT transistor as an amplifier, you're going to have a certain amount of current which goes into the base of that transistor to make it operate. And in the case of an NPN transistor, you've got a direct conduction path between the base and the emitter of the transistor. And so, of course, a certain amount of current is needed to operate the transistor, and that current will come from your circuit under test. But in the case of our field effect transistor, the gate is actually fully isolated from both the source and the drain, and the value of that insulation is very high, typically in the hundreds of megs or in fact gigohms. So when the gate of our field effect transistor is actually connected to the circuit under test, it draws absolutely no current from that circuit. Now although there is no DC current flowing into the gate of our field effect transistor, unfortunately we do have some capacitance between the gate and source and the gate and the drain, and that capacitance can in some situations also load our circuit, but maybe more on that later. So my active probe will be connected to the circuit under test via C1, which is a 100 picofarad capacitor. I think the main use of my signal tracer will probably be working on battery set radios. So I would suggest that C1 has a working voltage of something around 50 volts. That should cover most scenarios. However, there is also a small possibility that we might also want to look at signals in valve radios, and for that reason I actually chose C1 to have a working voltage of about 400 volts. Connected to the gate of our field effect transistor there is resistor R2, which is 10 megohm. The main purpose of R2 is to provide a discharge path from the gate of the field effect transistor, and also to pull the gate towards ground, which when you have no signal connected to the tracer will actually turn the FET off, so it won't draw any current from your battery. Resistors R1 and R5 connected between the source and the drain of the field effect transistor define the gain of the amplifier, and in this case it's set to just over 2. And resistor 1 is AC bypassed by capacitor C6. Capacitor C2, which is 10 nanofarad, is simply a coupling capacitor to the detector stage of our circuit. And germanium diodes D1 and D2 form a diode charge pump AM demodulator circuit. And this is simply a pulse-driven half-wave voltage doubler. And capacitor C3 10 nanofarads simply acts as a reservoir capacitor which is charged up by the action of D1 and D2, the charge pump. And resistor R3 is used to discharge that reservoir capacitor. To the right of the main circuit you can see that I've drawn some supplementary components. So starting at D3, which is a 1N4001, that's an idiot diode. That's simply in case I connect the power supply the wrong way around. In which case the diode will conduct and it will short out the power supply, hopefully protecting our field effect transistor. Capacitor C5 is 10 microfarad. It could be an electrolytic, although in my case I did use a tantalum because that's what I had to hand, and that simply provides supply smoothing. Now C4 is a 100 nanofarad ceramic disc. It's very important where you place this capacitor in circuit. It really wants to be across the supply rails but as close to the field effect transistor Q1 as possible. Well, I don't know about you, but I'm still of an age where I think LEDs are pretty cool. And for just that reason I've included LED D4, which is a green LED. with the current limiting provided by R4, which is 2K2. In the first prototype of this circuit I didn't have the LED connected, and I found that the supply current from the power supply was actually so low I couldn't measure it. It was less than 1 milliamp. However, with the LED in circuit, that supply current rose to 3 or 4 milliamps, so you might decide whether or not you want to fit an LED. So here we have the actual signal tracer probe that I built. Now as you can see, it is rather scruffy. Didn't have time to build it to scale or paint it. Well, I actually used a piece of Verboard to construct the circuit on, but you could equally well build it without a board, or maybe construct it dead bug style on a piece of copper clad board. And if you are going to use Vero strip board, as I've done here, there's one thing that you do need to do is, if I just turn the probe over, you can actually see that the area around the field effect transistor, especially around the gate, I've gone ahead and I've actually scraped away all the copper, because you don't want any ground plane or copper around the gate of the field effect transistor or around where the capacitor C1 attaches to the gate. And the reason for that is if you don't remove the copper strips from around the gate, what you're going to get is you're going to get some stray capacitance, and that's actually going to lower the impedance of the probe and stop it working quite as effectively. So hopefully you can see all I did was just took a Stanley knife blade and all the unused copper, I've just scraped it away. The signal from the circuit under test is going to come into the signal tracer. I'm just using an old nail here as a probe because, well, that's the best thing I had. And I went ahead and I've actually 3D printed these plastic end caps because I've actually designed this to fit inside a piece of 20mm plastic conduit. Now a plastic conduit might not actually be the best thing to put this in, and I'll demonstrate later that it does actually pick up quite a lot of mains hum because the circuit is such high impedance. Any electrical fields in the surrounding area, this thing will actually pick them up and amplify them. So in some ways a plastic enclosure isn't the best. You would be far better using a metal enclosure which you can then ground. But the reason that I chose to use a plastic enclosure, for me again, it's for electrical safety, because sometimes I do work in high voltage equipment and I don't like to have large pieces of metal poking around, because it would be very easy to touch a piece of metal. If this was manufactured from metal, it might be very easy to touch this against a 350 volt rail, and that could really spoil my day. So I tend to make anything that goes near high voltage equipment out of plastic, but that does create a problem with shielding, so we'll have to look at that shortly. So the signal comes in via the nail, it goes into our capacitor here, which I said earlier is a 400 volt capacitor, because you never know, I may actually use this in a valve radio for testing. So here's the resistor R2, which is 10 megohms, and that's actually connected to the gate of the FET. And you can see the FET itself is actually kind of mounted at a jaunty angle, and you can probably also see that I've actually got resistor R5 here just bodged onto the side of it. Well, there's a reason for that, is because I actually did change this circuit as part of the development. Initially R5 didn't exist. I was actually having this FET probe set up as a voltage follower, so R5 didn't exist, but I decided for my particular probe I wanted to have a little bit more gain. And of course, because I didn't design the layout to have this R5 resistor in, didn't quite have room for it, so I had to pull the drain connection of the FET. I had to disconnect it from the 9 volt rail which runs along here, and I had to reconnect it via resistor R5. So yeah, that resistor there is R5. On the other side here we've got resistor R1, and I also mentioned we need an AC bypass capacitor for resistor R1, so that's C6 under here. And again, the reason that it's bodged underneath the board is because I changed the circuit design halfway through. I didn't actually have room to fit it to the top side, but I'm sure if I was doing this from scratch again I would actually manage to get that capacitor in there somewhere. So yeah, not very neat. Now I did mention one thing to pay particular attention to is I did say that you have a 100 nanofarad disc capacitor, and that really wants to go across the supply rails, but you need to get it as close to the field effect transistor as possible. Then we've got the coupling capacitor here, which is C2. We've got our germanium diodes D1 and D2, and they're pushed over at somewhat of a jaunty angle, and the reason for that is just to keep the height of the circuit down so that we can actually get this into this 20mm conduit tube. And here's my 10 microfarad tantalum capacitor. You can just go ahead and use an electrolytic, but that's what I had to hand. And adjacent to that we've got resistor R3 and C3, which is the reservoir cap for the demodulation part of the circuit. And then just hanging out the bottom of the probe here, you can probably see we've got our very important green LED. So let's just go ahead and crudely assemble our probe here. So I've just got to stick it into its tube holder. So of course it's necessary to actually power the active probe, and we also need to connect the AF signal, the audio. You need to connect it to the input amplifier on the signal tracer itself. So to actually make that connection, what I went ahead and found was just an old pair of headphones, and I cut the headphone end off, and that just left me with a multi-core cable. Now, because this is just a junk box build, you're going to have to see what cables you've got available in your junk box, but really you do want to try to use a cable that's got some screening on it, and you do need at least 3 cores, because you need to shield the cable itself, the AF return from the signal tracer. That needs shielding. I've actually used the shield to provide the 0 volt connection to the active probe, and then you're going to need another wire to actually provide a 9 volt supply to this, because I've actually designed this to work on a 9 volt supply. So at the other end I actually reused the old stereo jack here. So as I say, it's got 3 pins on it. One of the pins on the jack plug is being used as the AF input. The other pin, one of the other pins is being used as a ground, and one of the other pins is actually being used to provide the 9 volt supply. And that, you can just plug that in here to the side of my Velleman K7000. Now I have actually got the volume turned fully up, and you can probably hear that it is actually producing just a little bit of hum. The hum seems to vary actually depending on what's switched on in my lab, because it does pick up noise, electromagnetic interference from the surrounding area. So if I actually just touch the tip of it, it'll probably get quite a bit louder. Now, as I mentioned earlier, because I've actually used a plastic tube rather than something that's screened, if I actually hold the probe near the end here, you can probably hear that the hum level from the amplifier increases. It gets a little bit louder, and that's because my whole body is acting as an antenna, and when I bring my hand close to the sensitive part of the probe, what's happening is the antenna, the electromagnetic interference which is being picked up by my body, it's being capacitively coupled via my hand into the probe here. So that's why you really want to include some shielding in the design of this probe. Now, if you're actually wondering how sensitive this probe is, all I can really say is it's very sensitive. So here's just a voltmeter, and so what my signal tracer probe is actually picking up there, it's actually picking up the drive to the LCD display. So you don't even need to make a connection to a circuit to do a little bit of testing. Now, regarding this problem of the unwanted mains hum and pickup, you can improve this quite considerably. So here's a piece of tin foil. So I've just wrapped that round, and you can actually hopefully hear. If you actually now ground this piece of tin foil, I'm now shielding the probe, it actually goes pretty silent. So I suspect earlier that you saw this little Zebedee spring sticking up from my piece of Veraboard here, and you may have wondered what it's for. So what I actually did was I went ahead and I've just folded over or rolled a piece of brass, and I've rolled that into a tube. So what I'm actually going to do is I'm going to actually stick this brass tube inside the handle of my signal tracer, and then this little spring here is going to press against the inside of the brass tube. It'll press against it, and this brass spring is connected to the 0 volts. So what it's going to do, it's actually going to provide a shield around our probe here, or certainly that's my idea. Now, unfortunately, this piece of brass, it may also short out against some of the other components, so I'm afraid I'm going to be a little bit bodgy, and I'm just going to put some tape around here just so nothing shorts out against the brass. So let me go ahead and do that. And again, not forgetting the all-important LED, got to stuff that into our end cap here. And now, in theory, we can just push this end cap on. That'll go in. And there we've got our fully assembled little signal tracer. Hopefully it's not going to hum anymore. Well, still a little bit of hum, but I think it's a lot better than it was. So let's just retrieve our little radio victim here. So is it tuned in? Yeah, it is tuned in, but it's not very good. Let's turn the volume right down on it. And let's first of all do what we did before. So let's go to the push-pull transistors here in the output stage, see what we can hear. Hopefully I can just get on.
ITV, my career isn't quite there yet, but I tried and I failed the technical portion.
So I hope you can hear that. This is actually an awful lot louder than the previous signal tracer was that didn't use the active probe. And in fact, this probe is so sensitive you can actually detect the audio waveform because you get a volt drop across the batteries here. So if we actually just go across the power supply rails, you can also hear the audio. Let's go ahead and find the detector stage. I think that was down here, wasn't it?
The Class A's and the instruments perfectly encapsulated their dramatic and ultimately doomed union, hitting a crescendo as John McBee's iconic.
So hopefully you can hear that's a lot louder. And now finally let's go to the actual RF input, which I think was transistor V1 here. Now you remember when we attached the last probe, our other demodulator probe, when we actually touched the one of the legs on the transistor here, the actual audio completely disappeared. It didn't work because the probe just loaded up the RF stage too much.
Just one change from the red eye to
Now, as you can probably hear, when we do actually probe the RF section of our radio, it does sound a little bit distorted. But the important thing here is the radio stays working. Before, when we attached the passive demodulation probe, it loaded the RF section up so much that the radio didn't actually work at all. The radio is still working, and we can clearly hear that there's a signal there, which is, you know, the whole intention of this probe. Now, I actually designed this probe to have quite a high input impedance. I wanted something around 10 megohm because I actually thought that the input impedance of the probe would really be defined by that 10 megohm resistor, which I think is R1 on my circuit diagram. But when I actually did test the impedance of the probe here, it turns out to be considerably less than I was actually expecting. So the actual input impedance of the probe is about 4.5 megohms. So remember that the basic impedance here of the actual signal tracer itself, it was only about 50 kiloohms. This is 4.5 megohms, so it's 2 orders of magnitude better. But it wasn't as high as I expected. It certainly wasn't 10. So I wasn't really sure what was happening. I mean, I certainly know that FETs have a reasonable amount of capacitance between the gate and the drain and the source, and I thought that that was the problem. So I did actually do some modelling, and it turns out that yes, that would reduce the impedance of the probe, but it wasn't reducing it to the 4.5 meg that I was actually measuring. So I wasn't really sure what was going on here. So I was speaking to one of my friends, Jeremy, who's much smarter than I am. So what my friend Jeremy proved in his little bit of computer modelling is what was going on, what was actually reducing the impedance of my probe much lower than what I'd designed, is something called the Miller effect, or Miller capacitance. So Miller capacitance, it's something that occurs, well, as I mentioned earlier, you do have capacitance between the source and the drain and the gate, but the effect of Miller capacitance, it means whatever gain you have in that particular transistor, it actually multiplies the capacitance, so it makes the capacitance seem more than it actually is. And of course that capacitance exhibits itself as a reactance, and that produces a lower impedance. Well, as you can see, I've gone ahead and I've set up our variable input impedance test board, and connected to the test board I've got my signal generator, and that's set to produce an output of about 2 megahertz with an amplitude modulation of 80%. To start with, let's just have a listen to the incoming RF signal. I don't know if you can hear that. I don't actually even have to touch the probe to the actual test point. I can actually hear it. In fact, let me just turn up the gain a little bit. just bringing the probe even close to the RF wiring, we can actually hear the signal there. Anyway, let's go to the input. So hopefully you can hear that's very loud. Let's go to the 1 ohm resistor. Very loud. 10 ohm resistor. Very loud. 100 ohm. 1k. 10k. 100k. Well, quite a bit quieter, but still pretty loud. Let's go to our 1 meg. You can still hear the signal at 1 meg. Let's try 10 meg. Still there. And let's try 20 meg. So it really is quite a vast improvement over a passive probe. What I can also do is I can just disconnect my signal generator, and what we'll do is we'll disconnect that and we'll replace this with my external antenna. And now what we can do is listen to several radio stations all at the same time. Now if any of you do decide to go ahead and build the little active probe here that I've designed, I would absolutely love to hear from you and how you get on. Leave a comment if it works, if it doesn't work, if you think it's rubbish, leave a comment, it's all good. Maybe you've got some suggestions of how we can improve this probe, and we could maybe have a look at that in a future video. But I think for today, that'll do. So until next time, bye bye for now.